Think about the mechanics of taking a massive string of data and forcefully crushing it into a tiny, dense package. A URL shortener does exactly two things. It takes a long web address and converts it into a short string. And when someone clicks that short string, it redirects them to the original destination. Look at the API layer. The post endpoint takes the original URL as a parameter, generates the short link, and returns a 201 created status. The GET endpoint takes that short URL and issues a 301 permanent redirect to send the user on their way. The logic here is trivial. You could write the code for it in a few minutes, but the code isn't the actual problem. To be viable, the system has to guarantee near zero latency and near perfect availability. A single server running this simple logic works perfectly in isolation, but the moment you expose it to modern internet traffic, it instantly collapses. Sustaining these simple functions under massive concurrent traffic requires an architecture designed specifically to function without a central point of failure. To build this, we must establish exactly how much traffic the system is expected to absorb. Let's assume we need to process 1,000 new URL generation requests every single second. Extrapolate that over a year, and we are storing roughly 31.5 billion new URLs annually. Using an industry-standard 10-to-1 read-to-write ratio, that means we also have to process 300 billion read requests in that same year. The architectural question becomes, how do we efficiently encode these billions of records into the shortest possible unique string? The standard approach is base 62 encoding. This uses a character set of lowercase a to z, uppercase a to z, and numbers 0 to 9. This diagram shows permutations scaling exponentially. Each position multiplies total possibilities by 62. 6 characters maxes out at 56 billion, falling short of our projection. A 7th character pushes the total to 3.5 trillion unique combinations, giving decades of runway. Establishing strict mathematical boundaries early on ensures the application won't run out of IDs, satisfying our foundational capacity requirement. The first step in handling massive traffic is basic horizontal scaling, placing a load balancer to distribute requests across stateless web servers. A naive implementation then points all servers to a central counter cache to assign the next base 62 ID. The flow seems logical. A server receives a URL, queries the central cache, and generates a short string. This central cache creates a single point of failure. A severe race condition occurs if servers operate at the exact millisecond. Both query the cache simultaneously, receiving the number 10. They generate identical short URLs for different user requests. Centralizing state in a horizontally scaled architecture creates deadly bottlenecks and data corruption. We have to completely redesign how IDs are generated. We replace the central counter with Zookeeper, a specialized service built specifically for distributed synchronization and configuration management. Instead of asking for individual numbers, we use range allocation. Servers request massive, exclusive number blocks. Zookeeper grants Server A exclusive rights from 0 to 1 million. Server B gets the next consecutive block, from 1,000,001 to 2 million. The performance benefit is massive. Web servers generate sequential IDs entirely within local memory, completely eliminating constant network pinging to a central database. If a web server crashes before using all of its allocated numbers, that specific block of data is simply lost forever. But remember our capacity planning? We have 3.5 trillion total combinations. Losing a few million IDs to server crashes is statistically irrelevant. By decentralizing state management through Zookeeper ranges, the system achieves immense horizontal concurrency without risking a single collision. We have solved how compute nodes generate IDs. Now we have to architect the permanent storage tier to manage the actual data. Because of our 10-to-1 read-to-write ratio, we face an extreme traffic imbalance. This requires completely separate solutions for saving data versus serving data. To handle raw data persistence, we implement a column-oriented NoSQL database like Cassandra. The rigid schemas and locking mechanisms of traditional relational databases would stall and fail under the weight of billions of constant writes. To absorb those 300 billion read requests, we deploy a distributed cache, such as Redis, alongside the database. The cache intercepts GET requests for popular URLs and instantly returns the long URL,
leaving the heavy Cassandra node completely untouched. We can optimize this further by tracking IP data to deploy these caches physically closer to specific geographic clusters of users. True high availability requires physically bifurcating data pathways, ensuring that massive write volumes never block read latency. There is a critical security flaw inherent in our current design. Sequentially generated IDs are highly predictable. A malicious actor who discovers one valid short URL can simply increment the final character to systematically scrape millions of private links. The primary architectural countermeasure is to append a random suffix to the end of the sequentially generated base 62 string, but this creates an engineering trade-off. Adding randomness significantly improves the system's overall security, but it forces the URL length to increase, working directly against the core functional goal of the application. We must implement strict rate limiting at the load balancer level, preventing botnets from executing DDoS attacks and flooding our servers with garbage requests. Designing for scale means designing for hostility. Raw performance must always be balanced against security, unpredictability, and infrastructure defense. This finalized architecture integrates load balancers, stateless servers, Zookeeper, and our bifurcated storage clusters. A POST request fetches an ID from Zookeeper, encodes it, and writes safely to Cassandra. A GET request hits the Redis cache and resolves in milliseconds, bypassing the database entirely. Moving from a local script to a system handling 300 billion annual reads requires shifting focus from simple string conversion to the precise coordination of distributed state and storage.